What's the connection between these four pictures? This one on the left at the top shows coal. On the right at the top, this represents crude oil. Bottom left, this represents natural gas. And bottom right represents peat. All four of these, what do they have in common? So the connection is that they're all fossil fuels, and that means they're all fuels which are found in the ground, like rocks are. Secondly, they're all finite resources. Finite resources are ones which are no longer being made or being made extremely slowly. And finally, they're all non-renewable resources. That means they're being used up faster than they are being formed. These are the parts of the C1 specification that I'm hoping to cover in this tutorial. Those parts which are in white are those which are at foundation level only, and those in purple are the parts which are at higher level. Crude oil was made millions of years ago by tiny plankton that lived in the sea. When they died, they fell to the seabed, and layer upon layer built up in the sand on the seabed, and after millions of years this changed into crude oil. Of course, we're using up this crude oil much faster than it's made, so we can consider that the supplies of crude oil are finite or limited. Therefore, once we have used them up, there won't be any more now for millions of years. As our oil reserves are used up, so the remaining resources become more difficult to find and more difficult to extract because they're less accessible. For example, they're in the seabed under deep oceans or found in the Antarctic, which is a protected area. And as the resources become more valuable, there's a conflict about whether they should be used for making useful substances like plastics or whether they should just be burnt as fuels, and indeed what we could use as a fuel if we weren't going to be burning fuels which are made from crude oil. Crude oil contains substances which are called hydrocarbons. This means that they're compounds of carbon and hydrogen only. And these structures here all represent different hydrocarbons. They all contain atoms of carbon which are joined together in chains and also have hydrogens. Now, crude oil therefore is a real mix. It's a mixture of liquids, gases dissolved in those liquids, and also solids dissolved in those liquids. But they all have this in common. They're all hydrocarbons. And it's the different chain lengths that allow them to be separated by a method which is called fractional distillation. For this next part of the tutorial, we're going to learn about how crude oil is separated into useful products and how the fractionating column works. This diagram represents a fractionating column which is used to separate crude oil into useful products. It's hotter at the bottom than it is at the top. It's said to have a temperature gradient. Crude oil is a mixture of liquids with different boiling points and also has dissolved in that solids and also vapours, so it's a real mixture. So the first thing that happens in the separation is that the crude oil is heated. It's heated in the furnace to about 350 degrees or so, and then enters the column at the bottom where it's very, very hot. Now, let's take as an example a fraction, a hydrocarbon which has a boiling point of 120 degrees. So it enters at the bottom, at which point it's a vapour. It's around 340 degrees at the bottom, so it's plenty hot enough to keep it as a vapour. So the vapour rises into the next section. Here it's 260 degrees, so it's still hot enough to keep it as a vapour, so it rises up into the next section. Here it's 180 degrees, still hot enough to remain as a vapour, so it rises into the next section. But here it's only 110 degrees. It's no longer hot enough for the hydrocarbon to remain as a vapour, so that means it condenses and then it runs off out of the column at this particular height and joins other hydrocarbons with similar boiling points. So the column yields different fractions with mixtures of hydrocarbons in each fraction, where each of the fractions contains substances with similar boiling points. Those which are at the top will be gases, and then they will become liquids until at the bottom there are these which such high boiling points that they're actually solids at room temperature. So the fractions with low boiling points exit from the top of the column, whereas fractions with high boiling points exit at the bottom of the column. This diagram shows some of the names of those fractions which you should be familiar with. This one at the top, refinery gases, is often called liquid petroleum gas, or LPG, and that contains substances like butane and propane. Then there's gasoline, as the Americans call it, or petrol, as the British call it, which is fuel for cars. Naphtha, which is used for making chemicals. There's kerosene, which is aircraft fuel. Diesel oil, or as Americans call it, gas oil, which is used for fuel for cars and buses and so on. There's fuel oil, which is used for fuel for heavier machinery. And there's bitumen, which is made into tar for roads and for flat roofs. And this picture here shows the size of a fractionating column. So in summary, the crude oil then is heated, and that makes all the liquids and solids evaporate and change into vapour. It then enters the column, mostly as vapours, and at the bottom of the column it's very hot. The top is very cool. This is called a temperature gradient. Then molecules rise up the column until they reach a section not hot enough to keep them as a gas, at which point they condense. The crude oil is separated into fractions, or parts of the whole as it were, so each of these fractions is a mixture of hydrocarbons with similar boiling points, and the fractions with high boiling points condense and exit towards the bottom of the column, and those with low boiling points condense and exit towards the top of the column. Now this diagram represents some of the molecules that might be found in liquid petroleum gas. Each of the carbons are joined together within this molecule by what are called covalent bonds. Now these covalent bonds are very strong, and when one molecule of the liquid petroleum gas is separated from other molecules of liquid petroleum gas, it's not these which are broken. These covalent bonds remain intact within the molecule. It's the interactions between one molecule and its neighbours which are overcome. Each molecule is attracted towards its neighbours by what are called weak intermolecular forces, and these weak intermolecular forces are easily overcome by higher temperatures. Therefore, when the liquid petroleum gas fraction is heated, the molecules are able to separate from each other because they have enough energy to overcome those weak intermolecular attractions. Because the molecules are very small, there are very few or very weak intermolecular attractions between the molecules, and therefore it takes very little energy to separate them. They have a low boiling point. This picture here represents some of the longer hydrocarbon chains that might be found, for example, in the naphtha fraction. These ones, because they have larger chains, have got stronger interactions between one molecule and its neighbours. Because these interactions are very much stronger, it takes a great deal more energy to separate one molecule from its neighbours, and therefore it has a higher boiling point. And because it has a higher boiling point, it will come out of the fractionating column a little lower down. So in summary, the longer the hydrocarbon chain is, the more of these weak intermolecular forces there are between one molecule and its neighbours, and therefore the stronger the overall interactions between each of the molecules. So more energy is needed to separate the molecules from each other, and therefore they have a higher boiling point. This is an example of a past paper question. The first question, A, says, crude oil is a non-renewable resource. Explain why. We might say it is used up faster than it is made. The next question says, crude oil is used to make useful substances in an oil refinery. Two of the processes that happen in a refinery are fractional distillation and cracking. Crude oil is separated by fractional distillation into fractions. Each fraction has a different range of boiling temperatures. Look at the diagram, it shows a fractional distillation column. Mark with an X the hottest part of the column. Well, in this case, the hottest part of the column would be at the bottom, so an X in this section, or indeed any area within this section or this part here will be fine for an answer. The final part, which I'll just reduce the size of it here, says draw a straight line from each fraction to the correct name. Now fraction A will be the lowest boiling point substance, which will be liquid petroleum gas. Fraction B, a little longer chain, will be a liquid at room temperature. That one would be petrol. Whereas fraction C, which has got the highest boiling point, would actually be a solid at room temperature, and that one would be bitumen.